Okay, so it's 6:30. I would like to welcome everybody to AI Swiss to this evening, where we'll have again a very awesome meetup about a subject which is interesting for all of us currently. It's all about tracking social distancing using computer vision. I love that kind of subject immediately when I heard it, and I thought it would be awesome for us to listen to the technical solution and all the business aspects. I'm happy to have two panelists today here with us who have joined us and who will guide us through the evening with the presentation. We will have Michael Gorkow, who joined us. He was a data scientist and is keen on developing innovative solutions, right, Michael?
Yes, definitely.
So you're the one who's taking us through all the technical stuff, and happy also to welcome Manfred, who is the guy who is actually transferring the business into the tech. So everybody who's in business will be just find an easy way to understand what kind of solutions might fit. Manfred, that's your daily business, right?
Yes.
Helping companies to find a way through the technology.
Yes, exactly.
So we already talked about where you're located. Manfred, you said you're in Vienna, it's in Austria.
Yeah.
So things are getting easier now with COVID-19.
A little bit, yeah. Everybody can go outside again, but cases start to go up now a little.
Ah, it's okay, starting to climb up again. Okay.
Yeah.
And Michael, what's Munich? What's Munich doing?
It slowly becomes better. So yesterday was the first day where the beer gardens opened up again, and I managed to get a seat in one of them. So beautiful day yesterday. But yeah, hopefully the numbers won't climb up here. But I think in maybe 1 or 2 weeks we can see what all these current actions will lead us to. But yeah, it's nice that you're already able to sit outside again.
Yeah, sure. I mean, sometimes it's hard just because of the sun outside. On the other hand, we know that it's still important to take precaution measures. One of the things which just happened recently, you might have heard it for those who are listening to German news. One of the logistic companies, DLD, just recognized that someone was infected by COVID-19, and they had to close the whole subsidiary. So we have an issue here on a very important business issue which might impact the economy again. That's why I think the subject is pretty interesting for this evening. So just for you guys who have joined, and I see still people coming in, a few things about how this all works here. We will have two presentations this evening with Michael and Manfred in that sequence. And if you look at the navigation bar from Zoom, you'll find that Q&A icon button. If you click on that, you can see that you can post questions to me. I will have it open all the time. So I'm going to listen to your questions, and I will pass it on to the panelists once we have the time during the presentation. We won't wait for the questions until the end. You can ask all the time. If you find something where you want to have more details, please just go ahead and send me your questions. They will be answered. Also, the session will be recorded, as I mentioned, AI Swiss YouTube channel. So the session will be available tomorrow. So coming back to our initial question, how can we track social distancing? That's one of the issues we are going to dig deeper this evening. And I'm happy to give Michael just the floor to talk about how do you do that technically. Michael, is it your daily business that you're actually coding stuff, or what are you doing daily?
I'm working as a so-called customer advisory for SaaS. So I'm responsible for talking with customers about potential innovative solutions. And currently my biggest focus is in the computer vision area. That's also the reason why I developed this demo for tracking social distancing on camera images. And yes, this definitely involves also a lot of coding. And as some of you have maybe read, I'm not only very keen to use SAS software, but I'm also a happy Python programmer. So you can expect to see some Python coding today as well. And I like to combine just those technologies. And yeah, that's interesting work.
Sounds awesome, Michael. So as you said, you will show us code as well?
Yes, I will. But given the time, I'm not going into every detail. This is just impossible. I had a quick look through one of my code files with a lot of intelligence in it, and it was more than 400 lines of code. And you can imagine this is definitely not possible to be explained in 5 minutes. But I will go briefly over the concepts and also briefly of how it would look like to code such a solution.
Sounds great. Will that code be available afterwards? Can we have a look at it, or is it?
Yes, everything is publicly available currently on my private GitHub repository, but actually, as some of my colleagues, especially from the US, notice that this is quite good work. We are planning to put it on our official SAS GitHub as well. As said, currently it's just a demo I have developed, but yeah, everything is already publicly available.
Sounds good. So if it's not public, will you just inform me about it so I can announce it on our channels? That would be awesome.
Yes, of course.
Thank you. So Michael, take the floor. It's your stage now.
Perfect. Then tell me when you see something.
Yes, presentation is
okay. Okay, perfect. So as said, what we are trying to do is using camera images and find out whether people actually adhere to the current distancing rules. I'm pretty sure I don't have to go into the details why we do this yet, because Manfred will later talk about it. But just to give a brief idea how I came to this small demo I've built here, we will have a SAS forum where we show our latest technology. And I was asked whether I could present something with computer vision. And looking at the current developments in like every country, I would say, there's a strong desire that we want to keep people with a very far distance to others. I think in Germany, currently, it's still 1.5 meters away. And of course, it will be very hard to track whether people actually adhere to it. And we have seen in the media that a lot of people don't do it, but it's just impossible to do it manually. I mean, we don't have so many police officers to monitor each and every place. And that's where the idea came to use computer vision in this case. As said, everything will be available on GitHub. So below here, you see also the GitHub link. And I've also written some articles on Medium about computer vision, in particular also about social distancing. So if you want to go deeper into it, have a look at the code, you can just follow these links and get more information about it.
On Medium, do you usually focus on that kind of subjects? Is it the main place for you to write?
Yes, we also have a SAS blog, also an official external one. But to be honest, my feeling is that if I want to get to know other people who are maybe not yet SAS customers or not even at all knowing SAS, it's better to go on more public areas like Medium. So that's the reason why I publish there. And also a lot of work I do is not only about SAS, but also about open source coding. This is the place to be for me, at least.
Thank you.
As said, social distancing. So the overall project goal from a technical perspective, as said, Manfred will cover the business aspects. So I'm only focusing on what I tried technically to achieve. And as you can see on the left, we have our very simple camera image where we see people in, I think it's a shopping mall. And what I wanted to do is use computer vision to actually perform 3 steps. In the first step, I wanted to do object detection. In particular, I wanted to detect people on images. This is a well-researched area, I would say, and there are a lot of demos where you can actually see object detection in practice. But of course, if you want to do the second step, meaning you want to calculate the distances between people, you have to know where the people are. So object detection is a mandatory task. Afterwards, I'm doing some distance calculations. And here you can already see on the image that I also wanted to make it visually appearing, what I calculated. So for instance, if you see people with like red to yellow colored, these are people who are very close to at least one other person. So for example, here on the right, I'm not sure, can you see my mouse cursor?
It's visible, yes.
Okay. If you look at the right, for example, there are two people very close together and they are marked with an orange color. So these people are very close together. And afterwards, I also wanted to do something called crowd detection. So if you look on the left side, for example, we have, I think 3 or 4 people very close together. And I also want to identify that because at least in Germany, you know, we had also rules about how many people are allowed to be together in public areas. And I think for most of the time, it was only 2 people. That's why I choose, for example, a crowd size of 3 or higher to be reported also with an additional blue bounding box. So these are the 3 steps I wanted to do from a project goal level. But I immediately noticed an additional problem, and that's what you can actually see on the right side. And I will go into more detail later, but just to give you an idea what the problem was. If you have a camera with a certain angle, it's very difficult to actually calculate correct distances. And that's the reason why I also wanted to build something called a bird's eye view. So it's like we are looking on the people from the top to actually get real distances. So on the right side, you can see this transformation, which is, yeah, like a top-down view to the people where we get the real distances calculated.
So
what I used,
how you use the colors, it's basically like a traffic sign, right? So red
yes,
is the warning, yellow is could be dangerous, and green is fine.
yes, everything which is green is good. Everything which goes to yellow or red is bad, because these are people who are very close to at least one additional person. And everything which is colored in blue, like this crowd here, is the crowd itself, also marked as an additional bounding box. And the crowd, in my case, is defined as 3 or more people. So for example, these 2 persons in the back, of course, this is not a crowd. They are missing at least 1 more person to be also marked with a blue box.
And did you install a camera at a real place, or where was it actually built?
So in this case, I just used a video from YouTube for the demo. Yes. But of course, the main idea behind it is that you can use maybe also cameras which are already in place. I mean, in a lot of public areas, we already have these camera solutions available, and we just have to connect the camera stream from these cameras to some kind of computer vision model to extract these informations. Does it answer your question?
Yep, absolutely. Thank you.
Okay. Some words about what I used to develop this this demo. And as said in the beginning, I'm working for SAS, which is a professional analytics software provider. But I'm also very keen in developing with open source software. So here you can see the 3 main components. One is called SAS Vaya, which is our enterprise analytics platform. And this one is actually used to develop the deep learning model for the computer vision task. And you can either do it with SAS coding, and to be honest, I'm not a very good SAS programmer, so I usually prefer to code in Python as well. And we have Python APIs to interact with this analytical platform. And everything you will see is Python code, but actually in the back end, we are working with a SAS environment here. Secondly, I'm using something called SAS Event Stream Processing. It's an engine which is basically very optimized to work with streaming data. And as you can imagine, videos are nothing more than just a number of frames coming in very quickly. So we are actually having streaming data here. In this case, I used it to develop the project itself, and what this means you will see later on. But for the last part, the Python part, as said, we have APIs utilizing Python to interact with SAS-Wire and also with SAS event stream processing. But I also used additional open source functionalities from Python to do some of the calculations. So this is a big combination of using enterprise software, which is very powerful if you want to deploy it in large scale, but also using very efficient and powerful Python packages, which can provide a lot of useful functionality, especially for things like distance calculation.
Do you offer an environment for people who want to test it, or how does it work usually?
I think we have a test environment available where you can, for example, use SAS-Wire, I think. The problem here is always that usually if you're working in the computer vision area, you want to make use of graphical processing units, GPUs, because otherwise training and also scoring takes very long. And this way, it's very hard to offer GPUs also for free on the internet. So following these steps, like at least training the model, is very hard currently if you're only relying on CPU power. Okay. We are starting with, of course, developing a computer vision models, like doing the first step. And in this way, we are going with SAS-Wire and the Python interface. In theory, how does it look like? And I try to explain it here in as simple as possible. On the blue box, you can see the training process. And usually we start with just collecting images from our camera. Afterwards, you have to label them because in most cases, computer vision models are still supervised models, which mean they rely on, in most cases, human annotated data. And in this case, what does it mean to label data? It means that you have to draw these funny looking bounding boxes around people to tell the model what it should learn to recognize in the future. And there are various tools to perform this labeling. One is the one I use is a very good one called Computer Vision Annotation Tool, CVAT, and it was open source by Intel, I think. So if anyone wants to start using their own data sets and have to annotate them themselves, I can highly recommend to use that tool. It's very good, especially if you're working with video images, with videos. After labeling your data, you train your model, and I will show afterwards very quickly how it looks like in our way. But what you get is the model itself, and in SAS terms, we always call it an A store, analytics store, which is more or less a binary file, which can then be used for scoring. Scoring, the green part on the bottom here, is a very identical process. So we are also getting camera images, but in this case, we are using our deep learning model to derive scores. And scores in this way means we are getting our coordinates for the objects. And coordinates means we have an X and Y value, as well as a width and height. So we know how big the object actually is. Afterwards, I also use some coding to visualize the results. So to actually draw these bounding boxes, because the computer vision model itself does not give you these nice visualizations. They just give you these scores and you have to do it on your own. As said in the beginning, training is usually done using SAS-Wire, which we will see very soon. Scoring, I've used SAS event stream processing to actually use our in-streaming engine. So
if you can just go back for a second, one note for everybody. If you check the chat window, I put in the link to the Github repository for CVAT, open source labeling tool. And we have one question from the audience. What object did you label? I think it's only people, right?
Yes, in this case, it's only people. But of course, the model itself is very generic. So if I label like different objects, I can also train the model to detect other objects as well. So for example, if you go to my GitHub repository, or was it me on Medium, I also have examples for example, aircraft turnaround management, where we are on the airport, and I detect different objects like airplanes, ramp loader, baggage trucks. And so the model itself is very generic. It's just what you train the model with.
Thank you.
For this case, I'm currently also developing something in addition, face mask detection. So imagine that you have very close camera shots where you can also see the face is very good. So not like in this case, I mean, you wouldn't recognize even as a human if someone is having a face mask or not, because the image is just too small. But if you have images where you could identify a face mask, you could also use such a model, for example, to identify people who are not wearing them.
Mm-hmm. What does the number stand for in red rectangles?
In this case, you should ignore them because in the labeling part, you're not adding these numbers. These numbers are coming actually from the distance calculation. So the people on the left, the two ones, are very close together, and I think it's 50 pixels. The one on the right is 60 pixels distance from the one on the left, and the one in green, I think a lady, is 126 pixels away from the lady in yellow. So that was a mistake by me, but yeah, during the during the labeling, you wouldn't have these distances yet. These are just derived later on from the model.
Yeah, sure.
Okay, so now I very quickly show how to train, in this case, a YOLO model in our software. And therefore, I would switch to a Jupyter Notebook, actually. So as said in the beginning, of course, you can code in SAS as well, and we have SAS Studio, our own integrated development environment. However, as someone who likes to also code in Python and to work interactively with results, I like to use Jupyter Notebooks as well. And what you see here is, yeah, as said, simple Python coding, but we are using different APIs to interact with our SAS environment. And I've included two of them here. So one is for our basic communication with the SAS environment, and the other one is called SAS DLPy, which stands for Deep Learning for Python, which provides a lot of functionalities with regards to deep learning, and computer vision is part of deep learning, so it makes sense to use that library as well. Both of these libraries are also open source on GitHub, on our official SAS GitHubs, but of course, in the end, you would need a SAS environment to actually make use of them, because they just connect to an enterprise environment. After importing all of them, of course, we will just connect to our environment, very simple. And then we directly start loading our images and labeling data. So for example, using DLPy, we have single functions which can perform a lot of work in the background, which you don't have to care about. In this case, for example, I want to create an object detection table. So a table which can be loaded into memory, and the model can train on that data. After loading it, of course, we also provide convenient functionality to just display what you have actually loaded. In this case, for example, you can see that I loaded pictures where we see already people which are marked by these bounding boxes, and can visually investigate whether the data loading was correct, whether I loaded the right data for the job I want to train on. It goes on with like simple analytics. For example, we want to sample our data in a training and validation partition. I can plot a little bit about the training data. You can see here, for example, I have more than 10,000 different objects in my training images, and around, I think, 1,500 in my validation images. So afterwards, I'm also able to verify on my validation data how good the model is actually performing. The model setup itself always depends on what kind of model you're using. In this case, we're using a YOLO V2 model, a very common model for object detection. And this model works with something called anchors, which actually are just predefined bounding boxes which help the object detection model to know how the to be predicted bounding boxes should look like. And we can derive that from our training data. We also have a very convenient function for that, which is basically just doing a k-means in the background to derive these anchor boxes. And if you visualize them, you can see that most of them look very similar. So maybe I could have just used less of them, but they are very close to what you would expect how a human would look like on an image. So they are very tall and very thin. So just like how a human looks like on images. Afterwards, you are creating your model architecture, meaning you add all these layers which your model consists of. And if you're using a very standard model like a YOLO model in our case, we also have pre-built architectures available. So you don't have to care about putting all the layers together. But in the back end, as you can see here, we are just putting layers on top of each other to create the final architecture. Of course, you have to define various parameters, like, for example, the number of classes. In our case, it's 1 because we are only detecting people. But for example, my airport example, where I also detect various other stuff, I think I have like 11 or 12 different classes to predict. I don't want to go into the details of every parameter here, but maybe just one important comment here. We are also making use of so-called transfer learning. So the basic idea is that you take an already trained model, take this weights and apply it to your new task. So your model does not start from zero, but also already has some knowledge about how to extract, in most cases, the features of images. And we're doing the exact same stuff here. So I've used a pre-trained model, which was trained, I think, on the ImageNet dataset, and just use it as a starting point for my model. Of course, I have to define what goes into the model and what the target is, and that's what I do here. I mean, I have the image as my input, and I have object detection targets as my targets. I can define various stuff which you always have to do in deep learning area, like your learning rate, number of epochs you want to train, all that what you also see if you, for example, use TensorFlow, Keras, or various other deep learning frameworks. So we also have the same stuff here. Here comes the interesting part where I said it's quite difficult to offer a test environment for it because I also make use of GPUs in the background to speed up the process. And this is a huge difference. Sometimes we have differences of up to a factor of 1,000 if you use GPUs and not only CPUs. So for computer vision, it's very important to have GPUs available, especially for training.
Just a quick question here regarding your current model. What kind of GPU did you use?
I used one from my gaming notebook, I would say. So it's GeForce RTX 2070 Max Q. So quite good one for notebooks, but of course there are better ones available. So if you're really performing computer vision on large scale data sets like the ImageNet dataset or something like that, I can highly recommend to go into the cloud and just use, for example, NVIDIA V100s, or even, I think there's just a new one which came out from NVIDIA, which is even more powerful. And yeah, you wouldn't train big deep learning models on a laptop at home in most cases. But for this case, it worked. Yeah, after defining all this stuff for the deep learning model, you can start actually training your model, and you can follow the process, how it improves over time. So as you can see here, these are all the different epochs the model was training. One epoch took around 3.6 seconds on GPU. If you go on CPU, you can expect it to be more than a minute, I would say, maybe even more. And of course, you're getting some information at the end, but more importantly, you can also visualize what you have trained. And here you can see that I think at epoch 150, our model did not improve anymore. So I could have maybe stopped here, or I would have to include maybe more data, choose different parameters. But yeah, you would have to investigate further why your model didn't improve afterwards, because as you can see on the numbers here, we're not going to zero, but we still have some errors left. So possibly you could also improve that model with more training data and more training time. Afterwards, we want to see whether our model learned what it should learn, and that's why I use this predict function to score our testing data or validation data. And of course, you can again display what you have scored, and here you can see the results. And as you can see, a lot of people are already marked correct. Not all of them. As I said, the model still has some errors, but I would say we are on very good track here. Of course, visually investigating just some images, yeah, is just a snapshot of the model. But of course, you can also calculate various performance measures. We have a function called evaluate object detection for that, which gives you various different measures. I have just chosen one here, which is the average precision, and plotted them with different thresholds. But as I said, I don't want to go into the details, just to give you an idea of what you could do while training such a computer vision model, and where you could try to further improve it. At the end, of course, we want to deploy our model for a scoring task. And that's why I just use a very simple function here to save the model in a format. I said in SAS, we call it an A store, an analytics store, which is more or less a binary file and can be shipped to any other application. So this is about training the model itself. As that code is available.
Bemekinas, who's joined us today as well. Bemek, I gave you, allowed you to speak up if you like.
Thank you very much. I would like to ask you about the data set. How many labeled photos do you have in data set? Because for me, it was very hard to label this big data set, because it requires a lot of working.
Yes, that's right. Let me see if I have, okay, in this example, I did not plot the number, but this can give you an idea. It's not the images, but the objects in the images. And I have around 10,000 objects in my training images and around 1,500 in my validation images. So it's huge, and still the model has some errors. So training computer vision model always requires a lot of data, especially labeled data. But for example, if you don't want to start from scratch, you can always try to use some pre-trained weights, especially weights which more or less were trained on the same task. So for example, if you want to detect face masks, which I currently try to develop, I'm using a model which was trained actually to detect faces. So the features the model extracts are already very similar to what I need for my face mask detection. So I don't start from scratch, but I use pre-trained weights to quicker get good results. But yeah, the labeling process is a big part, of course. There are some tools. I mentioned one, the computer vision annotation tool, which was open source by Intel, which can help you, especially if you have video data, because what you can do there is that you only annotate like frame number 1, frame number 10, frame number 20, and the people moving between these frames, they get automatically annotated by the software in the background, because it supports something called interpolation. So the bounding boxes between the frames are interpolated automatically, but still this is very limited, because you can imagine if a person is moving very shaking, then yeah, interpolation doesn't work anymore, and you still have to correct it by hand. But yeah, that's currently a big issue in computer vision always to get the training data.
Definitely. Thanks
Thank you.
for bringing up the question.
Okay, so this was how you would train such a model. At the end, we have an A-star file, a binary file, which can, given some camera data, predict our object coordinates. Now the general idea about how I wanted to implement the process overall. So as said, camera image, object detection, very clear. I think everyone can understand what's happening here. But then it gets a little bit trickier because in the next step, I wanted to do some distance calculation. And it sounds very simple. I mean, we have the coordinates and it's just calculating distances between points. But actually, it turned out that if I use the coordinates directly from the camera, I get very wrong distances. And this is due to the camera perspective. And due to that problem, I decided to go a longer way and use something called homography transformation. So to speak, I want to get rid of the camera perspective and have this bird's eye view where I view from top on the people to get these real distances. Afterwards, it's very simple math. I mean, we just have to calculate distances between points, and the crowd detection is also not very complicated, but the step in between was a little bit tricky, at least to come up with the initial idea. So one remark why it matters to use homography, and I took an example here from my training data. So we are currently looking at the bottom where I try to remove the perspective. And on the first image, you can see just a normal camera image, no transformation applied. And I have plotted two distances between people. In the background, you can see two people with, I think, 62 pixels distance. And in the foreground, you can see 356 pixels between them. Additionally, you can see that we have tiles on the ground. And I have marked an area using these tiles on the ground, which would represent a real world rectangle. So in the real world, if you are looking from top, we would identify this one as a real rectangle. I mean, I could just say that because I saw these tiles on the ground. If we calculate such a transformation matrix, homography matrix, we can actually map this image and try to correct the camera perspective. And on the second image, you can see what the result is. We have removed the perspective, and you can see that the former very skewed rectangle is now a very nicely shaped rectangle. So actually the transformation was working. I still have the old distances here, but if I also apply my distance calculation to the new image, to the new object coordinates given the transformation matrix, you can see that the distances are in real world totally different. So for example, on the bottom, we had 356 pixels, but now if you remove the camera perspective, you can see that we only have 149 pixels in total, which is not even half of the distance we would have expected just given the image. And in the background, the opposite is happening. From 62 pixels, it's in reality 83 pixels. So other way around, from a small amount of distance to a bigger amount of distance. And you can imagine this doesn't matter so much if you have very large thresholds. But if you talk about like 1.5 meter distance, this can be a huge difference in your analysis. So that was the reason why I decided to use this homography transformation to remove the camera perspective. As said, I don't want to go into the details of how homography works, but as you have seen here, a minimum of 4 points is required to calculate such a matrix. And usually you would derive them using some kind of automatic feature detection, like corner detection algorithm. And my demo right now, it's manually, but this is something I would say could be improved in future versions. Again, project setup. We have developed our deep learning model. We have a basic idea about how to design the streaming process. So we are using now this event stream processing in combination with Python to develop our process. And here again, I would look to show some code, and we have it here.
Quick question, Michael, just quickly from Mark,
Yeah.
was actually asking, so especially if a landscape changes, he was actually talking about a hilly landscape, so hügelige Landschaft. Also, if you have more difficult landscapes and if you are environments, so to say, in that context, did you test the environments as well, or did you just focus on develop the primary model?
I wanted to come to it later, but points 3 and 4 are ideas for improvement. And one problem is if you don't have a single plane area like the one I have in my video, you wouldn't need different homography matrices, matrices for each and every area. Therefore, of course, you want to have this automatically derived, giving some algorithm like a corner detection algorithm. And secondly, you want to have multiple of these matrices to cover different areas. You can also imagine, for example, stairs. You would need a different matrix for that as well. And my example is just very simple because, as you can see here, the area is a single plane area in real life.
So the problem is you can make a general model, that's fine, but at least you have to adjust the metrics for measuring the distance depending on the environment you actually have the video running, right?
Yes, yes. I mean, you can, of course, also try to ignore the bottom step here and use the coordinates from your computer vision model directly. But this usually will result in wrong distances. If you don't have a very bad camera perspective, this may be okay. Maybe if you have a camera which is like on top and films people from top, then maybe you can get rid of the transformation. But in cases like this one, the camera perspective ruins just every distance calculation. But as said, you could try to automate this process as well. I mean, we have technology which is able to detect certain features in images which can be used to derive homography matrices.
Thank you.
Yeah, the code. So actually, I'm trying to develop the process for scoring images now, given my trained model. Again, as said, we are using a Jupyter Notebook here, and I'm using something called thus-is-pi, event stream processing Python interface. I'm using OpenCV to actually do the homography matrix calculation. I think OpenCV, everyone would who is currently working in the computer vision area knows OpenCV very well. It's, I would say, the most important library out there for computer vision tasks, and some others which I don't want to go into details here. But just to give you an idea how you could try to calculate the homography matrix. As said, you need at least 4 points. You can use more, then the homography matrix will be more accurate, but 4 points is a minimum. You define 4 points on your camera images, and you define 4 points on the image where you want to map your points to. And in this case, it's my top-down view, or my bird's eye view. And yeah, then we have this very nice function from OpenCV called find homography, given some source points, some destination points. And at the end, we are getting something which looks like this. It's just a 3x3 matrix, which can be used, like I did here, to derive our transformed coordinates. So in this case, for example, if my model detects 100 as an X value and 200 as an Y value for an object, I put these two in my function, and the real world coordinates would be 130 and 236 for the Y value. Of course, in the background, this is happening for each and every object I detect, and of course also for each and every frame I score. So this is just a very quick example of how it looks like in the back. There's a lot more stuff to do, but this is the magic of the coordinate transformation happening there. The process itself is quite straightforward. So I start with some inputs I can give as a user. So for example, I define how big my input image is. I define what kind of images my model accepts. And for YOLO models, it's usually 416 by 416 pixels. Detect maximum number of 50 objects. I can also set some thresholds about what distance I want to consider in my calculations. So for example, if people are very far away from each other, I don't want to draw a line between them to show the distance, for example. It doesn't make sense. You just get a very crowded picture. The same goes for crowds. Of course, I only want to detect crowds if these are really people which are close together. And I can also set some threshold here. Minimum crowd size. I mean, currently I've set it to 3, but you can also set it to like 5 to only detect bigger crowds if you want. Also, the homography matrix, as you have seen here, is included as an input. And then, yeah, we start by defining our project. And first of all, we are just using our API to create an empty project. You can see here a project, and we have something called a query. A query is nothing more like a regular running process, which yeah, is doing some kind of calculations you define afterwards. And event stream processing works with so-called windows, and windows are just like functions which can be connected together. And my first one is called video capture, and it's just the source where we grab our frames from the video. So we will start with a very simple source window. It just receives one image. Then, as said, my YOLO model expects images to be in a certain size, and therefore I used a window, it's called calculate window, but uses a function called resize, and I resize every frame to 416 to 416 pixels. Afterwards, of course, we will have to load our deep learning model, and therefore I use 2 different windows. One which is like reading the model, and the other one which is actually deploying the model. So it is loaded into my GPU to score images. Then the most interesting part happens with regards to the computer vision task. We will add something called a score window, which uses our model and the resized images and scores these images. And then we are getting these X, Y, width, and height values for all the objects we have detected on our images. Last but not least, I've added an additional window which is doing the distance calculation given the objects we have detected. Then it also performs the crowd detection. And of course, I wanted to have it in a nice visual way where we, for example, have these different color schemes and so on. This is all included in the last window here. And the last one is actually a pure Python window. So in SAS event stream processing, you have the possibility to include Python as well. And you can see it here. I'm just including the function I've written, which is called social distancing pi. And okay, it's a little bit skewed up, but I also can set some inits like the distance, the maximum distance to detect, and the maximum distance inside crowds, and so on. So I'm just transferring all the initial variables also again to this function here, which is performing all these calculations in the background. And the end is a scored image, what you will see later on. Afterwards, we load the model, so it will be available for us. We create something called a publisher, which is nothing more than just a simple function which allows us to publish data to our project. And in this case, I'm using my YOLO model to be published into this process. I'm also creating, of course, the video capture publisher, which is responsible for transferring images to the project. And here I have the video publisher, publishing the videos, and I wanted to also see the results directly. That's why I used the video subscriber, which connects to my process. And yeah, that's it. Let's switch back to here. Some words about, before I show the final results of it, some words about what you have not seen here, because I showed you how to design the process itself, how to define windows to run all kinds of stuff, but I didn't go into the details of the actual distance calculation and also the crowd detection, because it's a very long and complicated code and would take too much time to go through it in detail. But the main idea is we get an image, we do object detection, or we get different coordinates, width and height values. We are using the homography matrix to get new x and y values, the real world coordinates. And then I use something called KD trees, which is very common, a very common function from SciPy, a Python library. And this one actually offers two very simple things to do. One is called distance matrix calculation. So given such values here, it automatically derives a sparse matrix of distances. So this one's very easy to do. The second one, I called it neighborhood lookup. Given one detected person, one x and y value, I can query this tree and derive all other objects which are in a certain range. So if you want to know more about it, definitely have a look at SciPy packages for sparse distance matrices, and also something called query tree from SciPy, which helped a lot in doing this these calculations in the background. Okay, last but not least, we can see how it looks like in reality. So this is the current developed demo. We have on the left side our annotated camera image. We detect people. We draw the lines between them, also with a small number indicating how far away they are from each other. And we are also having this crowd size detection, where you can always see how many people are currently detected inside the crowd. This dynamically adapts as the people are moving around. And on the right, you can also see the bird's eye view, like the view from the top. Additionally, you can see the small counter on top here, where you can see the total number of people, which could also be an interesting number if you want to do further analysis on it. Some ideas which I came up with, what I would like to improve. Of course, it's always good to improve the person detection. The model I've used here is a very lightweight model, but you could think about maybe some more advanced model architectures, might be an idea. Also, if you think about where we want to put these models into production, in many cases, it might be that we want to put it into production on edge devices, like maybe on the camera itself or on NVIDIA Jetson, something like that. And there you want to have very small models which can inference very quickly. So maybe you want to use smaller architectures for that. Then I already talked about 3 and 4. So if you have images with more than one single plane area, you want like to have different matrices, and in the best case, you derive them automatically given some like corner detection algorithm. And afterwards, of course, I mean, visualizing the results is very nice, and it's good to make people aware of the technology and to give them an idea of what we are doing. But you would need to include this data into, for example, meaningful reporting, use it for alerting, use it for additional analysis. So computer vision in this case should be more like a provider of additional data, which you otherwise would not be able to use. But it's not the goal itself. It's just a way to the goal. And I would like to give over to Manfred, because he is covering some of the aspects of what you would do with such data available and why it is important to use such technology. Just one comment before Manfred, sorry. I went over it very quickly, but as said, if you want to go into detail, watch the video again, have a look at the code, or even want to get more information about the ideas I had in mind, there is a link to YouTube where you can see the video. Everything is on GitHub already, and I've also published a story on Medium where I explain the basic principles of this demo. But now I'm finished with the technical part.
Thank you very much, Michael, for all those quite interesting insights. Looking at the links you provided on the last slide, is it something you can send me by email? I will put it on the YouTube page with a video recording.
Yes.
Would be
That's
awesome.
no problem.
So I think, yes, it makes sense to turn over to Manfred. So for everyone who has still questions, still watching the Q&A section, look at the navigation bar. You can actually ask your questions if you still have some, and we will still try to answer them. Manfred, so you actually, we want you to have or share more insights of the business aspects of all that.
Yes.
Really looking forward to what
So,
you have to share here.
yeah, so I'm going a little bit into detail. Can you see my screen, by the way?
It's black at the moment.
It's black. This is not good. Maybe I share again. It says that you're sharing the screen. Can you?
Yeah, it's still black.
Still black. This is not good.
But in case it won't work, it's not a problem, because since you sent me the presentation, I might also be able to show it from here.
Yes.
Let me check for it for a second. You can still try to make it happen.
Yeah.
No, it's black.
It's black. Okay. Then can you share it? And
I would say these are probably two exciting insights you're gonna share here.
yeah, that's why it's dark.
Yes, it had to be dark, definitely. So I'm going to start PowerPoint, but you can already start to help us in the context.
So the reason why we're doing all of this, I think, because it's a super relevant topic altogether. So it's really one of the first times that with a gaming notebook and a few lines of Python code, you can basically save lives, right? So I think this is a very great thing about this COVID situation. And we are working on this use case or on this problem already since about 4 weeks, I think we started. Because we're a global company, and of course from our global offices, we heard some quite strange reports 4 weeks ago, because not every country shut down, right? And for example, there's a company in the United States up in New England that did not shut down their business, because actually they ran the product is in very high demand at the moment. So they produced something that went up in demand, and they're at maximum capacity, and they were running through this whole Corona crisis. They kept producing. And what happened was that the owner got very concerned about the safety for his workers. So my part is really about worker safety today. And what he did is that he started to put a guidebook together for his employees, how to behave not to contract Corona. And this was basically a 50-page guidebook, but he still was in a situation that 32 of his workers, he has 400 workers in his factory in New England, but he has factories also globally. But still 32 of his workers got infected by COVID, and he was only able to detect 2 of them. So with his 50 good page guidebook and all the measures he put in place, he was only detect 2 out of 32 infections. So he got very frustrated with the situation he's facing, and that's why he asked us to help him with computer vision algorithms. So what Michael just showed, that's really at the core of the technology we're providing to him, to help him fight this virus and to avoid more infections in his factories. So maybe you can click 3 times now, then we should see the news articles that I just copied together just before the meetup. Now, 4 weeks later, this is not only the case in the United States, but also here in Europe, we have the same situation, right? We hear about infections in meat processing factories, but also in logistic centers. And in Austria now, I'm based in Austria, we have the military helping in the postal service. So, and if you think this further, this will become more and more relevant the more people go back to work. Yeah. And actually, I cannot see the presentation, but you should click maybe again to see the few bullet points that I put on. So we should still be on the first slide.
On the first slide, okay. You can't see the presentation at the moment?
It turned black, it kind of. But if you're on the first slide, it's fine.
It's the first slide.
Yes.
Yeah, I think Stefan, I think the problem is you are not in presentation mode.
I'm actually sharing.
Yeah, but what I see is the PowerPoint itself with.
Yes, not in presentation mode. That's right.
That's fine. Yeah, let's just leave it that way. Yeah.
If and see it, it's fine.
I think that's fine. Yeah. So the main problem that we see from this example is that people are not really used to keeping 2 meters of distance, right? That's not our habit. And what we find out now also is that it's not only 2 meters distance, it's also 15 minutes of dwell time that this virus apparently needs to have enough viral load to actually infect somebody. So it's very hard to contract it on public transport, but it's easy to contract it if you're within those 2 meters and spend more than 15 minutes time with somebody else. And of course, for the businesses, it's a possible disruption, and it's also a liability risk that is created, right? Because it's potential. There's the risk that workers start to sue their employers for not keeping them safe, and that's why this is a very valid use case. So can you go to the second slide, please? So what we are trying to do now is to create out of the technology that Michael was just showing a whole package of tools, yeah, that companies can use to keep their workers safe. Yeah. First is to create the situational awareness. So basically to use whatever data they have. So we try to use the existing camera infrastructure. That's why Michael used this homography matrix so that we don't have to install additional cameras. I think this is very nice. Yeah. And then to use this enriched camera data to calculate the distances, but also if it's available, for example, to use infrared cameras and measure the body temperature, so to have a live fever checker for all the workers in the factory. And taking this together, for example, we are also building traffic heat maps, so to show areas where people tend to spend the most time, to create something that we call predictive sanitation. So not to go away from cleaning plans that you say you clean your factory floor every 12 hours or every shift, every 8 hours, to clean more often in areas where there's more traffic, let's say, where people spend more time. And what we are also doing now is, because there's additional guidelines now for ventilation, because we know the virus is airborne, right? It's an aerosol. So to use, for example, CO2 sensors in the air that's getting ventilated out of the building, to detect if enough air is fanned into, if ventilation is enough in the building, yeah? If there's enough air going through the factory. And then all of this we pack into a dashboard, yeah, as Michael mentioned, to alert people in the factory, or it can also be a shopping mall, yeah, to send them, for example, a text message and say you just had, for example, 30 distance violations in the last hour, or take a look at the area A, yeah, because there's a high concentration of people there within the last shift. Yeah. So it's really about alerting people, creating awareness in management, but also to train workers and coach them how to keep those new regulations. So can we go to the next slide briefly?
By the way, that sounds quite sophisticated. So you're using IoT, as you said, in addition?
Yes.
The heat map,
Yes.
the dashboard. Do we have any illustration of a dashboard? Do you have a photo or something like that to share?
Yes, we have in a slide afterwards. I have a screenshot of this dashboard.
Okay. So we're on slide 3. I'm just listening. It was just interesting.
Yes. So this whole use case that we built here is basically built on the public regulations that are out there. Yeah. Because 4 weeks ago nobody was really concerned about this, so we pointed the customers we talked to the regulations that the public health authorities gave. Yeah. So this is, for example, from the CDC, the American disease control unit. There's very similar guidelines, for example, from the European disease control, but also from, for example, the German unions, the worker unions. And what they want to keep the workers safe is, for example, they say you should pre-screen, so you shouldn't go to work when you're sick, when you have a higher temperature. Yeah, and this starts at 37 degrees centigrade, for example. Yeah, I think it's 37.3, so it's not even a fever in a classic sense. Then, of course, to wear a mask, yeah, to keep your distance and to disinfect and clean the workspace. So this is the workspace, but also the common areas, like the place where you have lunch, or in factories, the areas where people change, yeah, where they put on their work clothes, for example. And the German health authorities even recommend that when you have a change of operators, for example, in a steel plant, yeah, when the shift changes, that the whole operator panels should be cleaned to avoid the virus to spread from one operator to the other. Yeah. So can we go to the next slide, please? Yeah, so the idea is that we have basically those 3 components, right, that I mentioned. So we have the social distancing, including the infrared screening, so the fever checks, yeah. The worker coaching, so how do we compile all this information that we gather to feed it back to the workers and tell them how to behave better, yeah, how to adapt their behavior to the guidelines that are currently in place. Yeah. The guidelines will keep changing. We're already observing this, yeah, that as we know more about the virus, there's more new guidelines and we need to adapt. And to have something like a proper ventilation module also. Yeah. This is the 3rd module. To feed all of this into a database and then give alerts and feedback back to the people that actually need it. So this can be the worker itself, can be a plant manager, or it can be a health official in the company. And what we then can do with this is we can ensure compliance with the rules that we set. Yeah, we can avoid that virus spreads. Like for example, in this one company in New England, yeah, where he tried hard to contain it, but it was apparently not possible. Yeah, with the traditional methods that are used. And also, what we can do is we can learn in our own environments how the virus spreads. So if somebody contracts the virus and you know in which area this person worked and you know what the distance behavior was with the actual data, you can learn how easily the virus spreads in your work environment.
This is an interesting point. So it was in one of our last sessions where we talked about the contact tracing app and the implications of it. If you say
Yes.
that could be a good base for research, so to figure out at certain places, certain events, or certain types of business, there might be a higher likelihood of getting infected. Is one of the ideas you already had to provide such data to research units, for example?
If it's possible, yes. So if the workers and the companies allow this, yeah, this is a topic that we will get back to, because we reached out to a lot of clients, and the sad part is that especially in the DACH area, there seems to be a lot of hesitance to use technologies like this one. So when you talk about using video footage to do surveillance on workers, you get into a lot of discussions with the unions. Yeah.
So I would say this typical challenge of doing that kind of computer vision stuff.
Yeah.
But just a question from a technology point of view, since you're actually detecting objects like people, you're not doing the face check, right? It's not about detecting people, individuals. It's just there is someone near to someone, and that's it.
Yeah. Yes.
Yeah, but still, it's like, I mean, still you are using the normal camera images where people are, of course, visible on. And yeah, we always have these discussions. It's very hard to go through them. But yeah, it's a matter of how good you explain what you're actually doing. And for example, the model we are using in this case is a model which is not even able to do identification of people. It can detect people, but only people in general. It cannot distinguish between different people, especially not in public areas where we have a lot of different people. I mean, you could train it to detect like 5-10 different people, given some training images, but this is not going to work on a large scale area, and we definitely don't want to go into this. Like I think in some areas in China we have
not in the DACH. Yeah, not in the
yeah.
DACH area, let's say.
Yeah,
we can trace people. Yeah, we can trace the people across the screen as long as they're on the screen. But when they're gone, they're gone. So it's just one person, and if the same person is coming back a second later, it's a different person.
So yes, there's no storing of data. It's real time, and it's, as I said, just for the moment.
Exactly, it's in stream. Yeah, so and
it's not
what
only
gets
in
saved.
stream, yeah, but also aggregated data usually. So you wouldn't
Exactly.
store for each and every frame all the objects you have detected, but usually you would aggregate the data maybe on a minute level, and also you're not storing each and every location, but maybe you just count the number of objects you detected or the number of violations you had against the distance rule, but you're not tracking on an individual level whether he or she was not adhering to the distance rule. This is not the plan, and wouldn't also not help in a lot of cases, I would say. It's more that you want to have general knowledge.
From a use case perspective, of course, you lose information, right? Because knowing, so for example, in the US, what we're doing, we're trying to combine this visual data with Bluetooth beacons so that you know who is where. Yeah. This allows a contact tracing within the confines of your company, of course. And if somebody contracts the disease, you can, in a very targeted fashion, go back and see who was this person in contact with. So you don't rely on the memory of the person. You can do this in an algorithmic fashion. But of course, this is not compliant. I would say, I'm not an expert, but this is not compliant to the European data privacy laws. Yeah,
Yeah,
but I think
definitely more difficult here. Yes.
Exactly. Yeah. But this is a very important point. So this is one of the main obstacles, I think, as in other areas of computer vision. Yeah, that it has a bad reputation at the moment. I think it's up to everybody, everybody here in this meetup also, to work on this and to stress the fact that for the model in this case, if you have a YOLO model, it's a person, and it's not possible to trace back who it is. Yeah. So it's anonymized data.
I think just a suggestion, as I'm also member of a German AI association. This is something we could bring up in politics as well, because it's something like where we should think about making it more publicly known that data is protected and that there are solutions which are certainly proved of something. It could be finding a label for it. So it might be easier to bring such solutions into the market. On another note, just because we're talking about it, there's a startup in Berlin I know of, which is actually blurring out faces. So they do the face, then they don't do the face detection recognition, task. We do the object recognition people, and they blur out the faces, so there's no privacy issue with that. But of course, and that's good that you mention it. We have a communication issue because we have tough privacy laws here, and people are more or less scared about what's happening with it unless there's a clear communication. And this is really hard for new solutions in the market. So thanks for bringing it up, Manfred.
Yes, and this is from our global perspective, right? Because this is quite easy to place in the US, for example. Yeah, there's less hesitation. Yeah, if you talk to people, managers or company owners here, you get a completely different feedback, and it could harm people in this case. Yeah.
Maybe just for all those who are listening and who are from different countries, raise your hand if you think you have something to share here, your experience in your country. Would be interesting to listen to that as well. Thanks, Manfred.
Yes.
I think we can just go forward.
So we can go to the 5th slide now.
Yes.
So this is now really the core of what we are trying to do now. Yeah, how we are trying to help companies with to restart now after this Corona pandemic or in this Corona pandemic. Yeah, you saw already Michael's computer vision demonstration, which is quite impressive. Michael already mentioned it. We're working now also on, let's say, a PPE reminder. So PPE stands for personal protective equipment, because what you're seeing, I see it all the time. I guess you also see it in supermarkets that people wear the nose mouth protection. They have it on, but they have it on their chin. Yeah, this doesn't make any sense, because then the virus can just spread. The aerosol.
And I always forget to wear them when I enter public transportation, to be honest.
So you're one of those guys.
Yeah, unfortunately.
So this is something we can also use computer vision for, right? We then have to condense those meaningful guideline violations, yeah, into a visualization. Meaningful, I want to stress, because just being close to somebody doesn't mean that you contract the virus, right? Research shows that you need to spend at least 15, so it varies between 5 and 20 minutes, I think, but you need to spend a certain time next to this person, right? And this is also where computer vision can help. This is quite hard, as we see from those contact tracing apps, to do with Bluetooth and so on. But with computer vision, yeah, with a camera and the homography matrix to correct distances, this is quite easy to accomplish. And then you can not only in a factory, but also in a public space. Yeah, for example, in an airport or train station, you can visualize and monitor those violations. And for example, a person responsible for an area can go in and put additional measures in place. Yeah, maybe to put lines on the ground, maybe to in a factory to inform the workers again, to keep coaching them. Yeah, and here, very small, you can also see this this heat map that I mentioned. Yeah, this is a dashboard that we created where you can see in red, yeah, the high density of traffic, yeah, of humans being there, spending a lot of time there to help people or to help companies deep clean their spaces better. So we're actually talking about deep cleaning now, which means to, for example, to put disinfectant on and leave it for 10 minutes and only then wipe it away. So there's special guidelines from the safe and health authorities how to clean spaces that are prone to COVID infection. Yeah. So to get away from the scheduled cleaning to a more predictive cleaning. And then another very interesting use case we've just started working on is this IR, this infrared camera use case. So some companies have started now to measure the temperatures of their workers at certain access points. So they reduce the number of access points and everybody gets checked for fever when he or she enters. And of course, this is a very tedious process because it's not only when people enter the building. For example, our customer in New England in the US also found out that it's also during break times, of course, that you need to do this because it only takes a few hours, right, between contract for the virus maybe to kick in and that you become actually infectious for other people. So this needs to be a more continuous check. Yeah. What we found doing this is that it's a little bit tricky. So in this image, it looks easy, yeah, because you can see this face is all red. You could just draw a bounding box around it with a YOLO model, and then take the maximum temperature in the face. In fact, it's not so easy. We found out that you need to do an upfront image and that you need to measure the temperature. So the best spot to measure the temperature is around the corner of the eye. So there's a small spot here where also the characteristics of the skin, because it blinds out reflections a little bit because the eye forms a little cave here. So this is the best spot to measure, and to do this properly, you need a few seconds, but it can be automated. And I think it can be a very important contributor to make workplaces safer. Yeah.
If you say take a few seconds just from a operational standpoint, so does it mean if you're entering your worker, you're entering into a facility or a shop or whatever,
Yes.
so you have to just stand there for a few seconds for the
Yes.
camera to, okay.
You have to stand there for a few seconds and you need to make sure that there's also no sunlight in the background because this can distort the image or the infrared measurement. Because you're talking about tenths of degrees here, right? So it's not a whole lot, because if somebody has 40 degrees fever, they won't go to work anymore. You're looking for slight deviations, and these are a little bit harder to detect, but it is possible.
It's also, it looks like it's a separate application of its own, right? And you had a
Yes.
separate testing for it. So you've compared it with measuring the temperature directly on people's heads. So how did you compare the data?
Sorry, how do you mean compare?
I was just asking about how did you test it? So if the model just
yeah.
numbers or so, did you
Yes.
compare it by having direct temperature testing with like temperature testing on the
in the ear, yeah.
In the ear, okay.
In the ear, yeah. Exactly. Yes. Good. So let's go to the next slide. So this was those few points were to avoid direct, let's say, direct contact, to avoid sick people coming to the company. Of course, this use case expands a little further because, as I said, it can be used to coach people. So we are not used to keep this distance, right? Especially in the Western countries. So I spent a lot of time in China, also in other Asian countries. There it's completely normal to wear a mask and to keep your distance, to wash your hands all the time, because they had more problems with epidemics and pandemics, right, in the past. So our application here is to use floor plans of factories. As I said, it can be also applied to retail, to shops or airports, and then to draw out like the area that is really so that the area that is really relevant for the specific worker, and to show on screens that they have available, or give them additional iPads, or maybe also use an app that we develop if they want to opt in, yeah, and give them a warning if there are distance violations in the area. So really to have a real-time warning or coaching that there is a problem with not keeping the distance. Yeah, it can be an additional expansion of this use case. So then let's go to the slide number 7. So this is the what I've put up here is the hierarchy of controls. It's called. It's also from the health authorities, the standpoint how you should keep the worker safety, right? It's basically a hierarchy of measures that companies have to put in place, and it starts with eliminating the possibility that somebody contracts the virus. So this just means putting workers in different rooms. Then there's the measure of substitution, and then there's a measure called engineering controls. So basically to take the hazard away from the people, and in this case it's an aerosol, so it's something that people breathe in and out, right? So one way of taking the hazard away is ventilating the rooms, yeah. And our customers asked us, so how do I know how to ventilate the room properly? There's a quite easy way to measure this. It's to take the CO2 level of the room and see how much the CO2 level increases when people are inside. And when it goes above a certain threshold, you just increase the fan speed. So it's a quite simple application of sensor-based control to avoid the virus spread. So you actually don't even need a camera footage for this. It's just an additional safety measure that companies can take. Yeah. Good. So this was the use case fleshed out. Maybe let's go to the last slide. We already had a little touch point with this. It's the privacy concerns. So we talked to a lot of our clients and in the DACH region, and the feedback was mostly that they are concerned with data privacy laws, yeah, doing something like this. This is very specific to European companies, I think. And the way we address those fears at the moment is, first of all, we say we use in-stream models. So basically, we don't even need to store the footage. What we do, what Michael showed before, this is a model that takes the video footage, extracts the data, and then the video footage is gone. Yeah, we don't need to save videos. If we want to save videos, of course, we can anonymize the results. So we can also do this. For example, in the bounding box, we could just put a blur on it. Yeah. And in case we want to go for mobile apps or Bluetooth beacons, also in Europe, which I think we won't, but One way to cope with this is, of course, to give the workers the possibility to opt out from this technology. Yeah? So it shouldn't be compulsory to use this, but they should have the option to say, okay, I don't want this. I don't want to be tracked through my workday. Which then, of course, also they give up the opportunity that they can be traced if an infection is found. Yeah. Yeah, so this was a short overview of what we are building and have built on top of the use case or the algorithm that Michael has programmed.
Awesome. Thank you very much, Manfred, for sharing all that. It was quite interesting. I think what I personally found just also scary a little bit is that there might be a good solution which could be used in a company context, but there are still too many concerns of how the data might be used and the issues involved with that. One question, if I look at the say the minimum solution of what you actually could offer, so just detecting if people wear a mask and have the appropriate distance between each other, how much would something like that cost a company to implement it in their environment? Do you have an idea already, or is it just?
Yeah, this depends. I think this depends how well we can detect the people. So it really depends on the lighting conditions, on the perspective also. Yeah. So it's basically comes down to how much effort we have to put in to train a model for those conditions. So the way we do this is we do a POC. So we take the video footage, we sign an NDA, of course, yeah. Then we take the video footage and Michael or one of his colleagues tries to put the algorithm on this video, and then we give a price indication.
So looking at the process of how such projects work, it's not a plug and play thing because we still need to train a model, right? So there's something like we start,
Yes.
how long does it take from implementation to, say, training a model in a mid-sized company? What do you think?
Yeah, so what we are aiming for is to do this quickly, right? So if we're lucky, we have something in place in 2 weeks. If it takes a long time, it might take 4 or 6 weeks. But this is the limit we give ourselves because this is a press time critical issue, right? We can't take too long.
Maybe one comment from my side, Michael. Yeah, it's not only about the training process itself, but it's also about what data the customer already has. I mean, if he has already labeled training data, it will be quite easy for us to train a new model on that. But if he only has camera footage and we also have to label them, or maybe with one of our partner companies, let this video footage be labeled, of course it takes longer. So this is also very important question to ask right from the beginning. What is the current status of the data? Is it labeled or not? And if yes, we are much faster. If not, yeah, definitely it will take some time to label this data. Additionally, it's very important to ask on how many different cameras you want to apply this to. I mean, you can imagine if you want to apply a model, for example, in a very dark room and in a very light room, it might have different performances on both of them. So you might consider to train 2 models, each for one of the rooms. So one for light conditions and one for very dark light conditions. And yeah, that makes it very difficult to say upfront how much time you will need.
And it's also, it depends on the perspective and the obstacles in the image, right? So now we see this perfect image from this shopping mall, but if you go to a store or a factory, you have obstacles in the way. So you have cranes, you have machines, right? So you also need to set up areas in the image that where you actually want to detect things. Those are all things that make it very use case specific, of course.
One of the questions from the audience was, do you use Mechanical Turk for the labeling? Or is it just partner companies with specialization in labeling data?
Mechanical Turk is not the only one who's providing labeling services. So I wouldn't say that we prefer to work with one of them. And usually we are also not the ones who like recommend to use one. So the customer can choose the labeling service as he would like. We just support in how we expect the labeling to be done and what the output format looks like. Besides to that, it's up to the customer who decides which service to use.
So as you do more of the quality control of what's the input data, and you work with them once you've controlled it or have control over it in the model. Okay. Interesting. Any more questions from the audience? Just take the time and put in the Q&A section. I'm still reading it if you have questions. So far, thanks again, Michael and Manfred, for being guests today. It was, I think it was quite insightful what you presented. I liked the discussion, and I would like to invite you both to continue with discussion, maybe as I said, with the German AI Association, because I think it would be interesting to think about finding some kind of quality labels for external communication to the market. It's a common problem for any kind of AI startup in that space, for computer vision especially. I think because there are so many privacy issues, and I think it could be something where we could have a joint approach, and where not a single company has to do it on its own.
I think this makes a lot of sense. Yeah.
So thanks again, and I just wish you a fantastic evening, and hope we can see each other again.
Yes, thanks for hosting
Thank you,
us.
Stefan, for
Have a good
hosting
night.
us.
So